Our last video presented a real-life example of how to use these concepts of nested logit to produce policy-relevant economics research. But we still haven't really explained where nested logit comes from mathematically, and that's what we're going to do in this video. We'll study Daniel McFadden's 1978 theorem that produces a function that can be used to construct any GEV distribution. This is the title page of that 1978 paper. And in particular, there's a theorem in that paper where he derives conditions under which GEV distributions can exist and what sort of properties they must maintain. So we're going to go through that in detail right now. We're first going to start with a variable y sub j, which is just the exponentiated observable part of utility for option j. And then we're going to consider a j-dimensional function g that maps rj to r that takes into account all of the exponentiated utilities. So g takes j different y's as arguments, where each y is an exponentiated utility. Then g needs to satisfy 4 different conditions, and if it does, then it can be useful for producing a GEV error structure. First, g has to always be positive, or at least non-negative. Second, it needs to be homogeneous of degree k, as the yj component of g tends to infinity, g needs to tend to infinity for all j. And any cross-partial derivatives of g need to alternate in sign weakly. So the first derivative needs to be non-negative, and then the cross-partial derivative with respect to another y needs to be non-positive, and so on and so forth. If all of these things are true, then we can define a new distribution function that is e to the negative g. This would be the CDF of the multivariate extreme value distribution associated with whatever g function we come up with. And the choice probabilities associated with this, with choosing the different options in this type of model, would be given by yj times gj divided by g. So here we're switching over from j to I to emphasize that this is the first derivative. So gi is the first derivative of g with respect to element I, whereas yi and pi are just going to be like yj and pj probabilities of choosing option I. So a little bit of notational switch there just to keep in mind. Perhaps an easier way of thinking about this is that pi is going to be the partial derivative of the log of g with respect to ui. So the key insight with this theorem is that log of g plus Euler's constant is the expected utility for any GEV model. And now that we have this result, let's use it to show that multinomial logit is a special case of this McFadden g function. So if we define g as the sum of the exponentiated utilities, that passes all of our criteria from the theorem. So g itself is always non-negative. It's going to have alternating cross partials because each component is additively separable. So we're going to satisfy condition 4. As uj goes to infinity, g is going to go to infinity, so that matches up. And then the other one is it's homogeneous of degree k. So that satisfies all of our conditions. So this is the derivative of the log sum of the exponentiated utilities with respect to uj, for example. Well, what are we going to get out of that? We're just going to get the formula for the logit choice probability. Now let's move to the nested logit. If we have, let's just suppose that we have 2 sets of nests labeled f and nf, and a option to pursue nothing, which would be n. This is what the g function would look like, because that's what the denominator of the choice probability for this nested logit function would be. And then for every option in the nest labeled f, what are we going to have? Well, we're going to have the choice probabilities, right? So again, we're taking it with respect to the log of g, right? So all of these components are entering the log. That's why they're all going to enter the denominator of the choice probability, because the derivative of the log of x is 1 over x. And then by the chain rule, we need to bring down this lambda and then exponentiate to lambda minus 1. And then we also need to take the derivative with respect to what's inside here, which is going to be 1 over lambda times exponential of u over lambda. and then the 1 over lambda from this derivative cancels out with the power rule lambda that we brought down. And so that's how we get this choice probability. So hopefully that gives you an appreciation for Daniel McFadden's work and the contributions that he's made to the world. In the next video, we're going to show how this McFadden GEV property has been put into action by multiple researchers, and also use it to think about how we can improve analysis of the market for artificial intelligence large language models today. So hopefully you'll enjoy the next video, and I hope to see you there.